And last but not least, we have Black Cat 2. You know the drill by now. This is Husky Hacks, and we are covering the final challenge that I wrote, and really the final challenge in general for the Huntress 2023 Capture the Flag competition. And let me tell you, when this one dropped on the final day of the challenge, it was just fireworks. It was so much fun watching everybody race to try to solve this one. Again, this is one of the hard challenges, and I would say that this is probably the hardest challenge in the Capture the Flag. So without further ado, let's go ahead and download it and let's get working. It's actually a pretty quick download this time, so let's look at what we've got. We've got Black Cat 2. Let's unpack and take a look. So remember, this is a sequel because this is Black Cat 2. We have kind of a similar setup to Black Cat 1. We have the victim files directory, which has all of our encrypted files in it, but this time we don't have a note, we have decryptor.exe. So when we double click on decryptor.exe, we read our ransomware note, and Cosmo's back, and it looks like he's quite mad. Heard some crafty analysts found a way to break our encryption algorithm, bravo. But guess what? We spent a ton of time redoing it, and it's unbreakable. Pay us the bitcoins, you get the idea. So two things to note here. This is not just a static note. This is a form. This is actually a .NET form, and we'll go into what that means here in a moment, but the two things of note here are the full path to victim files. So you would want to just put in wherever your victim files directory ends up, you would put that in as the full path towards that directory, and the decryption key. So if we just fuzz these parameters, let's see what we can do with decryption key. And if we try to submit it just an arbitrary key of just a couple of A's, it says key must be 64 characters. And so whereas Black Cat 1 was about known plaintext and breaking a weak XOR cipher, this key has to be 64 characters. So that's 32 bits. So a 32-bit key is virtually impossible to break by brute forcing. So that rules brute forcing out of the question immediately. Otherwise, there's not much else going on in this program. We just have the decrypt button and the two form fields to fill in. And so if we were to do strings against the binary, against the decryptor in this case, what we're left with is a pretty good giveaway that this is a .NET compiled binary. And so we can also run like the file utility, which I think would be a little bit easier, but we get some of the dead giveaways that this is .NET. Super clean string decompilation. We can also find things like mscore lib. So we can either run the file utility on Unix, or we can run the strings against this. But essentially, one of the first things that you want to do is kind of identify what type of file you're working with. And though this is an executable, not all executables are created equally in terms of reverse engineering. When we find out that this is a .NET compiled executable, the absolute first thing that you should do is open up dnspy, because we are working with a .NET binary and we can reverse this thing back to its near source code. And that's going to be incredibly important as we head into breaking down this binary and figuring out how we're going to solve this challenge. And of course, before we get any further, in the victim files, we have a few other interesting files here. They're all art pieces, except for the flag. And if we look at flag.encry, I mean, we've got absolute garbage here, but notice how each of these are different art pieces as well. And they're in order, alphabetical order, that's going to come into play here in a moment. But in any case, let's go back to our decryptor. So once we open up dnspy, let's open up our decryptor binary inside of dnspy so we can take a look at the code inside. We've got clean decompilation because this is the .NET framework. Just a very high-level overview of this. The .NET framework will compile code, but it will also translate it into essentially bytecode, which is called the intermediate language, the IL. So IL is extremely readable and has to exist inside of the continuum of the .NET framework. So IL code exists inside of the kind of like continuum, the runtime of the .NET framework, and it's instead of like assembly, which is extremely verbose and hard to read, IL is essentially near source code when you look at the decompiled output. So when we go into decryptor.exe, inside of the binary, we've got three different areas to look at. So we've got decryptor util. I'll make this a little bit bigger. Decryptor util, form 1, and program. Form 1 is actually what we see when we double click and run this program. So if we go back into the desktop and we go into decryptor and we double click on that, what you see here is our .NET form. So this is the code that organizes and presents the .NET form. And there's not a ton going on. A lot of this is boilerplate, but we do get to the button one click function. And in the button one click function, we have a couple of bounds checks on the two form fields. So we have the full path to victim files, which is taken from that form field. And we have text2 here, which is the key. And so if you don't put a key in, it says there's no key provided. If the key is less than 64 characters, it says it must be 64 characters. But if you satisfy both of these requirements, then it will say running decryption routine. It calls decryptor, the class of decryptor util, and it calls the decrypt files function. And then if we go back to what we just saw, then it will say files decrypted. If there are any exceptions, it prints those out. So this is the sauce right here, because the key and the full path to the victim files directory are passed in. And if we go in here, we can start to tease apart what this is doing. So inside of the directory, it takes this is the decryptor utility, remember. So we can assume, hopefully, that the encryptor utility is doing something similar, just in reverse. So the decryptor takes every file inside of this directory that has a .encry extension, and then it'll put that into a list. And the directory.getFiles function does not guarantee the order in which these files are placed into the list, but it turns out that this is actually going to be in alphabetical order, and that's going to be important here in a moment. So if there are no files to be found, this will return outright. We also instantiate a string called text, which is null. Now, this is all decompiled output, so the variable names are not going to be super helpful here in the first place, but let's just follow it down. For every file in the array of files, here's what happens. We instantiate a new string called text3, which is set to nothing. If text is null, so if this is the first time around in this loop, we are going to make text3 the decryption key. The decryption key in this case is passed in as the argument. So remember, that came in from the form. Text3 is set to the decryption key. Let's assume that this is the first time that we have done this. We're going to skip this else block here because that doesn't matter yet. And then we're going to go here. Text4 will be the combined path of our directory and the file name without extension plus decry. So we're setting up the write into the decrypted file at this point. We then run the AES decrypt file utility from this class, which takes in text2, text4, text3, and a hard-coded initialization vector. So let's recap again. Text2 is our file going in, or in this case, because this is the decryptor, this is our encrypted file. Text4, in this case, is the out file, the decry file. And text3 is our decryption key itself. All of these are strings. All of these are going into AES decrypt file, as well as a hard-coded initialization vector. If we go to AES decrypt file, this runs an AES CFB mode decryption routine on that file. So in goes the encrypted file, in goes the password. We've got a hard-coded initialization vector, and then we decrypt the files and then write them out to the output file. Now, the intention here is that this AES decryption and the corresponding AES encryption are built with CFB mode. And that could maybe in some circumstances, especially because this is also zero padded, possibly lead to some kind of crypto attack. But that's not the actual approach here. And so you may have burnt a little bit of time looking through this decryption routine and figuring out if you have to approach this from a crypto perspective. And I assure you that is not the solution here, because if we go back up to that if block that we skipped, so if the text is null, then the text is the first decryption key. Every other time, the decryption key is the calculated SHA-256 hash value, the string of the SHA-256 hash value of the decrypted file. So you had to reason through the code a little bit, but if you imagine that the files are running in a loop and every time a decrypted file is run, it takes the SHA-256 of that decrypted file and uses that SHA-256 value as the decryption key. So the issue, the vulnerability here is in the implementation of this right here, because this is a wacky, wacky way to do AES encryption. In most cases, you're going to see some kind of ransomware AES encryption work file by file, code an initialization vector into that file, and then generate a unique key for each of ththose files, and then try to extract that some way. When we're working with this encryption decryption routine, this becomes vulnerable because if we know the SHA-256 sum of the first file that was encrypted in any given directory, then we have the key because we feed it the first key and then it decrypts the first file. And then the second file is decrypted with the SHA-256 hash of the first file. And then every corresponding file continues after that point. It's like dominoes, basically. So if we have the first SHA-256 of the first file, we have the key and we can decrypt every single file in any given directory. So that begs the question, do we have that information? If we look in the victim files, we have A Sunday Afternoon on the Island of Le Grand Jatte by George Surratt. And it also has this kind of like GUID looking unique ID thing, and it's a JPEG. And then we've got a couple other paintings here. Café Terrace by Van Gogh, Guernica by Picasso. We've got Impression Sunrise, Monet, and Wander Above the Sea. So this now effectively becomes an OSINT challenge, because if you can find the first file, which is A Sunday Afternoon on the Island, if you can find the SHA-256 hash of that file, then you have the key not only for this one, but for every single file in this row, including the flag. All right, so how do we find this file? A lot of players approach this by Google dorking. I am told anecdotally that Google dorking is a lot less effective now that Google started implementing like weird AI in its searches, which seems to be problematic. But I have also heard anecdotally that some players found effective Google dorks for this. I just don't have those on hand to show you. So if you found one, please comment it. I would really appreciate to see that. However, if we look at some of these paintings, I mean, what would be the natural solution here to find out where all of these paintings came from? I mean, my thought in this case was to Google top 100 paintings. And so we get the Google results, but we also get the first result here at ATX Fine Arts. And if we go into ATX Fine Arts, we can then cross-reference each of the encrypted files in victim files with the different paintings in here. So let's see if we have A Sunday Afternoon. And of course, we've got a nice little pop-up here, which is great. So we've got A Sunday Afternoon. Okay, so that's check one. Let's go see if we have Café Terrace. I think we actually passed it. Let's see here. I guess we can also just Control-C, Café Terrace. All right, so we've got Café Terrace at Night by Van Gogh. And we've also got Guernica by Picasso. And there it is. And then we can check the other ones as well. But basically, we could go one by one and make sure that all of these paintings are actually present here, and they are. But that itself does not prove that this is where the files came from. But the only one that we're really interested in is the first one, A Sunday Afternoon. So if we find that one, which I think was scrolled down here a little bit. So if we find this one, because this is the first one in the alphabetical order, let's inspect the element on this painting. And we see that we've got the image source link here, which I can copy this link address, and let's open it up in the terminal. If we look at the link here, we get the full name of this file right here. So let's take that and let's open up Notepad. And we'll paste that one in, and then we can go over to the victim files, and let's take the name of the first victim file, and let's see if they match up. And there is a 1-for-1 match. So the idea here was that you would have to find A Sunday Afternoon, but you'd also have to correlate it to this GUID right here, which is the exact GUID that you get if you just right-click and save as from the art site itself. So one other potential gotcha here is that this comes across as a JPEG, but if you try to right-click and save image as, you actually get a WebP. Now, this was inconsequential. You know, the file type, the file data itself is what determines the SHA-256 sum. So we could actually just change this to JPEG, but it did throw a few people off that this was actually downloaded by WebP. But we don't even need to call it anything. We could just call it key if you wanted. The point is to download this too. And also another gotcha here, you have to think about how the user would have downloaded this. This is a ransomware incident running on a Windows operating system. So you'd imagine that they were browsing from Windows and their user agent would be Windows 10 or something like that. And if you downloaded it from like, any other kind of user agent, there was a chance that you weren't going to get this file itself. But if you got this file and we save that to the desktop, we can then run the get file hash utility commandlet against this file hash. And let's pass in a Sunday afternoon, etc., etc. And here is our SHA-256 hash value. And so this right here, if you reverse engineered the program and you understood how the encryption decryption routine was implemented and the principal flaw in its implementation, this is the key right here. So we can copy this and we can go back into our decryptor utility, which is actually right here on the desktop. And let's fill in the blanks here. We can paste in the decryption key, which is the SHA-256 sum value. And then all we have to do is point this towards victim files. And so let's decrypt. It'll say running decryption routine, files decrypted. And let's take a look at what we got. We now have all of the decry files, and the only one that we really care about is the flag. And that is the flag right there. So that was the approach to solving Black Cat 2. It's a little bit of OSINT, it's a little bit of RE, it's a little bit of malware analysis. I like to say that, like in any good video game, the final boss here is kind of like, it combines everything else that you've learned along the way. And so this was the final boss of the Huntress CTF. It was a little bit of a combination of a bunch of different skills that you may have picked up along the way. I hope you enjoyed it. That's all for the walkthroughs that I'll be doing for the Huntress CTF. Please leave comments, tell me what you liked about the CTF, tell me what you didn't like. And if you played the CTF, please fill out the feedback form. And I'm really looking forward to hearing everybody's solutions for this one and all of the rest of the challenges. So thank you. Thank you for watching. Take care of yourself, and I will see you next time.